Most people see equations as empty black symbols, but for me, a J is always light tan, an N is violet blue, and an X is dark brown. Those are not metaphors. Those are real colors, rooted in biology. I have a rare condition called grapheme-color synesthesia. Over 300 million people worldwide have some version of it, yet almost nobody in physics talks about how it changes what becomes possible to discover. While my students at Princeton saw chalk on a blackboard, I saw entire landscapes of shifting color. Sometimes the colors harmonized, and sometimes they clashed, and that visual harmony, or dissonance, told me whether my math felt right or felt wrong. Could this strange way of seeing actually reshape how reality is understood? Let us find out. Grapheme-color synesthesia is not a poetic quirk or a trick of memory. It is a neurological reality, stamped right into the wiring of the brain. The word itself comes from Greek, syn for together, aesthesis for sensation. In my case, it means that every time I see a letter or a number, my brain automatically overlays a specific color, as real as if it were painted there. I could never switch it off, and I never learned it from colored magnets or childhood games. It has been there as long as I can remember, as involuntary as breathing. Scientists have tried to unravel what is happening inside the skull of someone like me. In 2011, researchers at the University of Bergen put synesthetes into MRI scanners and watched what lit up. They found that the same brain regions responsible for seeing actual color, areas deep in the visual cortex, also activate when a synesthete sees a black letter that their mind insists is violet bluish. The strength of this brain activity tracks how close the physical and synesthetic colors are. If the real ink matches the imagined hue, the signal gets even stronger. It is not imagination or metaphor. The color processing machinery is firing as if the color were right there in front of your eyes. Roughly 4% of people, about 300 million worldwide, have some form of synesthesia. Most never talk about it or even realize it is unusual. The colors are consistent, automatic, and stubbornly personal. Ask a synesthete to pick the color of a letter or number, then come back weeks later, and you will get the same answer almost every time. This is not a party trick. It is a testable, repeatable phenomenon, mapped right onto the brain's own circuitry. For me, that means equations are never just black marks on a page. The brain's color machinery is always working overtime. When I lecture or work through a problem, the colors are not a distraction. They are as much a part of the mathematics as the symbols themselves. Science has peeled back the skull and found the evidence. Synesthetic perception is as real as anything else you see. The question is, what does it mean for the way a mind like mine approaches the world of physics? Princeton, 1939. I was 21, a graduate student under John Wheeler, wrestling with the foundations of quantum electrodynamics. The halls were quiet at night, but my mind never was. When I opened John K. and Emde's book of mathematical tables, Bessel functions did not just sit there as black and white formulas. They moved. The light tan J's, the violet bluish N's, and the dark brown X's seemed to swirl and dart across the page, each carrying a weight and a presence of its own. The colors arrived uninvited, as stubborn and precise as the numbers themselves. Wheeler would scribble equations on the board, and I would see more than just the structure of the math. Each symbol had a personality, a kind of visual signature that made the patterns stand out. Sometimes, when an equation did not feel right, it was not a logical flaw I noticed first. It was a visual disharmony. The colors would not fit together the way they usually did. Maybe the tan of the J would clash with the brown of the X, or the whole thing would seem off balance, like a painting with the wrong palette. That was when I would stop and retrace the steps, looking for the mathematical slip hiding in the colors. I never told Wheeler about the colored letters. It felt private, almost secret. I did not know if anyone else's mind worked this way or if it even mattered. But when I looked at a page filled with Bessel functions, the patterns leapt out. The colors made the relationships between terms easier to grasp. I could spot repetitions, symmetries, or subtle changes in an equation because the hues would shift and snap into new arrangements. It was like having an extra sense for the music of mathematics, one that played in color, not just sound. This way of seeing was not just a curiosity. It shaped how I attacked problems. Instead of grinding through lines of algebra, I would look for the visual flow, the way the colors grouped or separated. If something felt ugly or out of tune, I would know to dig deeper. The equations became landscapes I could wander through, searching for the right path, not by logic alone, but by sight. That is how the seeds of my later methods were planted, not by memorizing rules, but by following the colors wherever they led. In 1948, something happened in my mind that changed how physicists everywhere approached the quantum world. I was no longer satisfied with equations as lists of symbols. The colors and shapes I saw in my head needed to be set free on paper. That is how the Feynman diagram was born. Instead of lines of algebra, I began sketching little pictures, arrows, squiggles, and loops, each one standing for a particle, a force, or a process. What looked like doodles to others were, to me, just the natural way the pieces fit together. The patterns were obvious when you could see them all at once. Not everyone understood this at first. Julian Schwinger over at Harvard preferred to wrestle with page after page of dense equations. His approach was pure logic. Every step spelled out, no shortcuts. But I wanted to see the whole dance at once. Freeman Dyson, working at the Institute for Advanced Study, took months to realize that my diagrams were not just pictures. They carried the same weight as Schwinger's algebra. He later said that what I had drawn in a few strokes was hiding all the mathematical machinery he had spent weeks untangling. Years later, researchers at the University of Toronto found that people with grapheme-color synesthesia are better at spotting hidden patterns. They do not just process information, they see connections others miss. Maybe that is why the diagrams came so easily. They were not a trick or a shortcut. They were a new language born from the way my brain insisted on seeing structure and color where others saw only black and white. When the Nobel Prize arrived in Stockholm in 1965, it was not just for solving equations. It was for showing the world how to see physics differently. Most people trust their senses to tell them what is real, but the universe does not care about what we can see or hear. Take the mantis shrimp. This little creature packs 16 types of color receptors in its eyes, compared to our measly 3. It swims through a world painted in colors I cannot even imagine, ultraviolet and polarized hues that do not exist in my mind's palette. What would physics look like if I could see what a shrimp sees? Maybe the hidden patterns would leap out, obvious as a red apple on green grass. That is the trouble with perception. You only get the world your brain is built to handle. In 1974, philosopher Thomas Nagel asked a simple question. What is it like to be a bat? Not just to imagine echoing in a cave, but to actually live inside sonar, to sense the world in pulses of sound instead of light. His point was that some experiences are locked away. No amount of cleverness or thought can open the door. There is a whole spectrum of reality that slips past us, not because we are not smart enough, but because we are not built for it. I am not the only one who has glimpsed a different slice of reality. Daniel Tammet, born in London in 1979, sees every number up to 10,000 as a unique shape, color, or texture. In 2004, he recited Pi to 22,514 digits, each one a step through a mental landscape of shifting color. Nikola Tesla, working alone in New York in the 1890s, could build entire machines in his mind, running them for months before ever touching a single part. Some brains are tuned to channels the rest of us cannot pick up. Maybe the next breakthrough in physics will not come from a new equation, but from someone who simply sees more of what is already there. Some minds really do see what others cannot, even in science. Today, as we chase the universe's deepest puzzles, it is not just intelligence we need, but new ways of perceiving. The next breakthrough may depend on a brain wired to see what the rest of us never will.